Hello and welcome back to another video. In this video, I will be discussing lift. Many people incorrectly believe that lift is produced because of the equal transit theory. The equal transit theory states that lift is produced because the top of the wing is longer than the bottom of the wing. The air going over the top of the wing and the air going under the wing have to reach the end of the wing at the same time. This would mean that the air going over the top of the wing has to go faster than the air going under the wing because the air going over the top of the wing has to travel a longer distance in the same amount of time. This would produce lift because the air molecules that are going faster would be more spread out and would therefore have lower pressure. The higher pressure air under the wing would then try to move towards the low pressure air above the wing, but the high pressure air would just hit the wing, which would produce lift. However, this is not true. Scientists know that the equal transit theory is wrong because the low pressure air moving over the top of the wing actually reaches the end of the wing before the high pressure air does. Scientists also know that the equal transit theory is incorrect because planes are capable of flying upside down. If the equal transit theory were correct, then planes that were flying upside down would actually be forced into the ground because of their lift. Many people believe that the equal transit theory is correct because many textbooks, websites, and YouTube videos say that is how lift works. In fact, I used to think that was how lift worked until I made this video. I even said that equal transit theory was how lift worked in one of my older videos. Lift is actually produced by airfoils, aka wings, deflecting air. The air changing direction is an action force, and lift is the reaction force. Most wings are curved so that the air will be deflected downwards. However, this doesn't answer our question of how planes can fly upside down. Not all planes can fly upside down. For example, an Airbus would probably not be able to fly upside down. Fighter jets, on the other hand, can fly upside down because during upside down flight, they maintain a high angle of attack so that the wings still deflect the air downwards. One airfoil that most planes have is called a symmetrical airfoil. A symmetrical airfoil is an airfoil where both halves are the same. This means that if the airfoil is pointing directly into the airstream, it produces no lift because each half deflects the same amount of air. However, if it is ever positioned slightly to the right or left of the airstream, then it will produce lift in the opposite direction because it starts deflecting air. Symmetrical airfoils are most commonly used as the vertical stabilizers on the back of planes. Their job is to prevent the plane from side slipping, which is when the nose of the plane starts to move to the left or right. Occasionally, they are used on the sides of rockets to keep them stable during flight. For example, the Saturn V had symmetrical airfoils on its side, although the Saturn V symmetrical airfoils also had flaps to make the airfoils unsymmetrical if need be. The flaps on airfoils are used to make them unsymmetrical or switch the direction that the wings are unsymmetrical in so that they produce a lift in a different direction. Symmetrical airfoils are actually quite important in the aerospace industry. You might look at a rocket and think that there aren't any airfoils on it, but rockets are actually symmetrical airfoils. The Falcon 9 would be unable to land so precisely if it wasn't a symmetrical airfoil. The grid fins and cold gas thrusters on the top of the Falcon 9 booster will turn away from the airflow so that it starts producing lift that will move the booster's trajectory closer to the landing zone. Also, partway through the booster's descent, the Falcon 9 will perform a dogleg maneuver, which is a maneuver used to change the booster's trajectory. Before the dogleg maneuver is performed, the Falcon 9 is actually on a course that will make it miss its landing zone. This is done so that if something fails, then they won't perform the dogleg maneuver and the Falcon 9 will crash into the ocean, killing nobody. The Falcon 9 isn't the only symmetrical airfoil used in the aerospace industry. Capsules are also symmetrical airfoils. While capsules are descending through the atmosphere, they are producing lift that is going upwards. This makes it so that the capsule will spend more time in the upper atmosphere, where they can bleed off speed while experiencing less atmospheric heating. Engineers also use several methods to make aircraft more stable in flight. The first one of those is dihedral wings. Dihedral wings are wings that slant up so that the top is higher than the base. This means that if the plane ever rolls, a roll is when an aircraft turns without changing the position of the cockpit, then the plane will revert back to its original position. It does this because the plane is now rolled slightly over. Now that the plane is rolled, its wings are creating lift that isn't vertical, which means that this plane is now going in the direction of the side of the plane that has the lower wing, which means that the lower wing is now deflecting air from in front of it and to the side of it, which means that it's deflecting more air and is therefore producing more lift, so that it produces more lift than the other wing and the plane starts to roll back to normal. However, dihedral wings will also make you experience less vertical lift because the lift produced by dihedral wings is not entirely vertical. It will make planes roll slightly slower because the wings will just try to counteract the roll. Another cool trick that engineers use to make planes fly faster is swept wings. Swept wings are wings that are tilted either forwards or backwards, although right now I will only be talking about wings that are swept backwards. When wings bend air, it accelerates. This acceleration can cause the air to exceed the speed of sound, even if the actual fuselage of the plane has not exceeded the speed of sound. The speed at which that occurs is called the critical Mach number. Once the air has exceeded the speed of sound, the air is going so fast that the other air molecules cannot move out of the way in time. This means that the air will be compressed and will form a high-pressure area known as a shock wave. The shock wave will then break up the flow over the wing so that it produces less lift. In early airplanes, this was not a problem because they would never get close to the critical Mach number. But towards the end of World War II, planes started to exceed their critical Mach number while diving. When this happened, the plane would start to nose down because the front wing would produce less lift. This lack of lift would make that plane enter an even steeper dive, which would make it go even faster, and eventually the plane would crash into the ground, killing the crew. Swept wings are usually used to fix this problem because when air travels over a swept wing, the chordwise flow travels perpendicular to the leading edge of the wing, and the spanwise flow travels down the length of the wing. Because the air is divided when it travels over a swept wing, then less air will be accelerated, so higher speeds are needed to reach the critical Mach number. However, the spanwise flow adds up throughout the length of the wing, so that there is more spanwise flow at the tip of the wing than at the base. The spanwise flow will increase the boundary layer at the tip of the wing. A boundary layer is an area just above the surface of a solid, where the fluid is moving over the solid moves slower. An increase in boundary layer makes the wing create less lift because there is a larger barrier between the airflow and the airfoil. This means that the airplanes with swept wings will stall at their wingtips before they stall at their bases, and the tip of the wing is where the ailerons are. And ailerons are used to control roll, so airplanes with swept wings will lose roll control at low speeds. I was unable to find an explanation for why spanwise flow increases the boundary layer of wings. My assumption is that the engineers don't actually know why spanwise flow increases the boundary layer of wings. That is actually quite common in the aerospace industry. Fluid dynamics are incredibly complicated, so a lot of the time people are just testing designs in wind tunnels to see if they work. Have a nice day and don't die.